Hello everyone, welcome to this fifth video of this concurrency control, and in this video we are going to cover the topic of optimistic concurrency control and pessimistic concurrency control. Please watch the video where I explained you read uncommitted and committed and repeatable read and serializable to understand this topic. So what we are going to see that read uncommitted and read committed are the combination makes it optimistic concurrency control, and repeatable read and serializable combination make pessimistic concurrency control. So let me make you understand this point. I made one arrow for you, concurrency from low to high. So it means as we are moving from pessimistic to optimistic, the concurrency is increasing. As we are moving from serializable, repeatable read to read uncommitted to read committed, our concurrency is increasing. So what we studied a definition of concurrency, that our system should be capable of doing multiple transactions at the same time. This was the definition of the concurrency. So let's understand the point. So first point is read uncommitted, or we can say it as highly optimistic system or high concurrent system. Why? Because in the read uncommitted, we are saying that suppose there are n number of transactions are going in our system, like transaction T1, transaction T2 and transaction T3, writing on the same row, they are reading on the same row, they are doing anything. We are not taking any lock on anything. We are not taking any lock on that particular row. What will happen? We'll reach into the problem of dirty read, non-repeatable read, phantom read. We'll going to get so many problems, but that makes our system highly concurrent. We can do it. If we are making a system that is only reading the data, then we can of course do it. Okay, there is no problem. We can make our system highly concurrent with read uncommitted because there is no locking involved in our database. Now move to the second point, that is read committed. So read committed is saying that I am going to take a shared lock as I am reading the data, but I will going to take an exclusive lock when I am writing the data. So now let's make an again let's understand with an example. So suppose there is a T1 who is writing a data on a row number 1. So what will happen? The row number is getting to be locked. If the row number is going to be locked, can any other transaction can read that particular row? And the answer is no. If no other transaction is going to read that particular row, then they all the transaction have to wait, or either they are not going to happen. That makes our system little less concurrent, because what the concurrency was saying, that these transactions should happen. Okay, our system should be able to perform multiple transactions at the same time, because but now what is happening, because of this locking thing, all the transactions is waiting right now, and when all the transactions are waiting, that is making our system little slow and little less concurrent. So that is the example of read committed, and we can say it as low optimistic in nature. Now third point is repeatable read. So what repeatable read was saying to us, that we are going to take a shared lock on the complete transaction. For like when we are reading it, we are going to take a shared lock. Whenever we are going to write on any transaction, we are going to take an exclusive lock for the complete transaction. So again, what is going to happen? If suppose I am reading the row 1, no other person can also read the data. If I am reading the row transaction T1, no one can read the data as well. In the read committed, at least someone can read the data, but in the repeatable read, no one can read the data because I am the one who is reading the data. And suppose in this repeatable read, if suppose I am writing on any row number 2, no one can also write on that data. That makes our system low concurrent. That makes our system little more slow. And then that is why we will say it as low pessimistic concurrency. Now in the serializability, we have all the properties of repeatable read. We have the complete lock on the transaction while reading. We have the complete lock on the transaction while writing. Now what will happen in this scenario? We are having a range lock also. So suppose if I take a range lock from 0 to 1000 row. So now what will happen? If I have a range lock at this time, so no one in the system, if I am the user 1, I am the transaction 1 is going on, I have taken a range lock from 0 to 1000 row. Can anyone perform any action from 0 to 1000? The answer is no. The system will become very slow because no one can perform any action on these 1000 rows. That will make our system very slow, or we can say low concurrent, and that is known as highly pessimistic concurrency control. So now let's see some examples of optimistic concurrency control and pessimistic concurrency control. So I draw one small diagram for you. Here I am saying that there are two transactions, transaction T1 and transaction T2 happening at the same time. So internally, optimistic concurrency control maintaining a version in it. So what this version will do? At time T1, I made a to read call to our system. Transaction T1 gets this data, id equals to 1, status equals to free, and version equals to 1. Transaction T2 also get the same data, status equals to free, version equals to 1. Now what will happen? At time T2, transaction 2 made a write call to the system. Now at time T2 what happened? id equals to 1 and status equals to booked, make a write call to the system and change the version equals to 2. And now what happened? We committed the transaction at time T3. Now what will happen? At time in the transaction T1, if we again make a read call, what we are getting? We are getting the version equals to 2. This time we will say we cannot commit this transaction because we are getting a different data, because the version has changed. Previously the version was 1, this time the version was 2. Hence we reach into the problem of dirty read. So this is the only problem that the optimistic concurrency control is solving, that we cannot do a dirty read. All the other problem, like if it is if I take an example of read uncommitted, we have to face this problem. If we like repeatable read, we have to face the problem. In the phantom read, we have to face the problem. In read committed isolation level and read uncommitted isolation, we are going to face all the problem except this problem, that is optimistic concurrency control is solving. Other than that, there is no problem optimistic concurrency control is solving. And what else optimistic concurrency control is doing? It is making the system very fast. So this is the only problem that is solving. It is making the system very fast. And there is one more thing, there is no deadlock in the system. Like transaction 1 and transaction 2 are not even dependent on each other. If they're reading the same data, they are not dependent on each other. They can create a problem, but they are not dependent on each other. Like they can do whatever they want. Okay, so this is the example of optimistic concurrency control. Now let's understand the pessimistic concurrency control. So our pessimistic concurrency control tries to say 2-3 things to us. So it will say the transactions will happen in order. So if T1 will complete, then T2 will start. If like in an order, like we can just also say that if T2 will complete, then T1 will start if they are dependent on each other. And if our system is highly pessimistic, then we have a concept of range locking as well, that we have studied in serializable. So let's understand the problems in this and like pros and cons of this whole pessimistic concurrency control system. So I made one diagram for you. So if we have a two transaction T1 and transaction T2, if I'm like reading a row A, can T2 can read a row A? If I'm updating a row B right now, can T2 update the row B? The answer is no. It is not even possible because T1 is working on these two rows, T2 cannot work on these two rows right now. When we have committed this particular data, like when we committed this transaction 2, transaction 1 completed, after that T2 will start and perform the action. This is why this is making our system little slow, because now they are not happening in parallel, they are happening in on like these transactions are going to happen in an order. First T1 will complete, then T2 will start. That will make our system slow, but it will keep our data right in our database. This is a pro, that it will keep the data right in our database, but the con is that it will make our system slow. Now let's understand the problem of deadlock in our pessimistic concurrency control. That is, if there are two transactions that are happening in in parallel, in transaction 1 first of all read the data, read A, and transaction 2 first read the data B. Okay, this is possible. So transaction 1 takes the lock on row A, transaction 2 takes the lock on row B. But transaction 1 wants to write on the row B and transaction 2 writes on the row A. Is it even possible? Now we are in the situation of a deadlock. A is taken by transaction 1 and we cannot write it. This is not possible. B is taken by transaction 2, transaction 1 can also not write it. These both the transaction are in the deadlock state. They both are waiting right now, and this is not going to be solved. This is the problem of deadlock, and we reach into this territory of in the pessimistic control. So our pessimistic concurrency control is going to give you the problem of deadlock, but it solves the problem of data. So when you need a system in which data is very important, you need our data to be consistent every single time, then you have to choose pessimistic concurrency control. And if you're making a system that is reading the data value is not that important, at that time you can choose the optimistic concurrency control. This is all about these two things. Thank you so much for watching me, and bye bye.